Let's dig in. Building stateful workloads in Kubernetes. Here's the part where I tell you I'm definitely going to post the slides on my site tonight. You're going to look tonight, tomorrow, next week, next month. In about 3 months, you're going to get tired of pushing a refresh and you're going to email me. And in 6 months, I will promptly reply and say, no, I'm definitely going to post them on my site tonight. And I'll never post them at all. I've been in that spot and I really don't like it, which is why you can go to robrich.org right now. Click on presentations right here at the top. Here's building stateful workloads in Kubernetes. And here's the slides that we're going to look at right now. They are online right now. So feel free to go to robrich.org, and any of these blue links will click through to the URLs of the things that we're talking about. While you're here on robrich.org, click on About Me, and you'll see some of the things that I've done recently. I'm a Microsoft MVP. I'm a friend of Redgate. AZ GiveCamp is wonderful. AZ GiveCamp brings volunteer developers together with charities who otherwise couldn't afford software services. We start building software for them Friday after work. Sunday afternoon, we deliver completed software back to the charities. Sleep is optional, caffeine provided. If you're in Phoenix, come join us for the next AZ GiveCamp. It is always a lot of fun. Or if you'd like a GiveCamp in your area, hit me up by Twitter or by email, and let's get philanthropy installed in your area as well. Some of the other things that I've done, SQL Source Control Basics, Gulp. I was a core contributor on version 2 and version 3. And kind of my claim to fame is I replied to a .NET Rocks podcast episode. They read my comment on the air, and I got a mug. Woohoo! So there we go. I love Sean's comment yesterday. I got mugged. So let's dive into Kubernetes. Building stateful workloads in Kubernetes. We talked about this guy. Let's start off with stateless Kubernetes, because that's kind of the easier end of the things. In stateless Kubernetes, we have a user that hits an ingress controller, a service, then round robins across all of the pods. Each pod wraps a container. We got this. This is, everybody's Kubernetes 101 talk. And this we know how to do. This is pretty sweet. But our applications probably look a lot more like this. We have our pods and our containers and our service and our ingress, but we also have things like, well, what is the domain that comes into the ingress? And we may have a database cluster that needs to be able to prop up, and different parts of that database need to be able, or different machines in that cluster need to be able to interact together. We have configuration data of how we authenticate to that database. We may have file storage where we store uploaded information, and we need to get a path to that, together with the domain and the certificate associated with that ingress. All of these pieces are the state within our application. And these are the pieces that we're going to talk about today. How do we add state to our application? Well, let's take a step back and talk about what is state. What is state? Not these states. We're going to talk about state in an application. State is anything that lives beyond the current lifetime. Well, what is that lifetime? Is it a request and a response? Is it a machine restart? Is it a function call? A great way to make state persist beyond a function call is to put a property on that object, so that then I can read into that property anytime I re-enter that function. Taking a look at those, how do I create a mechanism that is beyond a request and response? Well, I'll probably save something to the server that I can pull back, maybe to a database. How do I get things beyond a server restart? Well, I need to save it to the database, but I need to make sure the database isn't on this machine. So that's really cool. We're going to look at stateful mechanisms, and we're going to look at how we store state inside Kubernetes. When we looked at the state, we looked at things like configuration, secrets, data stores, file stores, and Singleton services. Let's unpack Singleton services, because that's kind of interesting. So a Singleton service, if I have in my database an auto-incrementing primary key, I need something that is aware of all of the pieces of the database and can increment that primary key. Similarly, if I need to run a month-end report, I need to have all of the data for all of the customers to be able to create that month-end report. A singleton service is something that needs access to the entire state of all the things in its domain so that it can make some critical business decision. And in this case, these singleton services are probably stateful services, since they need to persist that data, that information. Now, sometimes we have singleton services that are only specific to a single thing, like the auto-incrementing ID in a table. Its domain is only that table. It doesn't need to know all the things of all of Kubernetes. So these singleton services, data stores, file stores, secrets, configuration, these are the things that we're going to look at today. How do we bring these types of state into Kubernetes? So first up, kubectl get all. Now, as the name implies, it returns everything, except for it doesn't. kubectl get all very specifically does not return stateful resources. And they made this design decision because they wanted to protect these stateful resources from prying eyes, or protect you from automatically deleting things that you couldn't just regenerate. So kubectl get all does not return all. As you grab these slides from roberts.org, you can click through each of these blue links to get to the issue that was filed saying, hey, kubectl get all doesn't return all. And the Stack Overflow question as well that says, hey, can you fix it? And the answer that they always come back with is, well, kubectl get all is kind of deprecated because it doesn't, but it was designed specifically not to return everything. So how do we return everything? Well, kubectl API resources will list all of the resources that we've defined in our cluster, including custom resources. So if we pull in a service mesh like Istio, and we have all of the custom resources associated with Istio, they will also get returned in kubectl API resources. So here's the script, kubectl API resources, pipe it to awk, pardon me, pipe it to awk that will grab the first line, or the first phrase, pipe it to grep -v name, so take off the header, pipe it to zargs, pipe it to zed, to sed, to comma separate them. So now we have a comma separated list of all of the types in our cluster. kubectl get that, and now we get all the things. Not that unlike saying kubectl get svc comma pods. Now we get all the services and pods. kubectl get all this thing, we'll get everything. So yeah, typing that whole thing every time is probably more than you want to do. This is a good place for an alias. Grab this, alias it in your shell, and now you can get all the resources, all the resources, and get at stateful resources as well. Any questions so far? Awesome. Let's dive in. So the punchline there, many of the things that we'll see today aren't in kubectl get all. But if you use that alias, you'll be able to see all of the things. Volumes. Here's the first thing that we'll dig into. Volumes allow us to do durable file storage, to store files beyond a pod restart, and to share files between pods. This is really cool because as we persist our data into a volume, we know that it will be there as the pod starts back up. It's basically a symlink from storage elsewhere into the container at a particular directory. Now, because it's a remote file system, the local file system locks don't really apply. So the local file system may choose to lock that file, but the file isn't locked according to other pods or the host file system. So as you're doing this, just understand that file locks won't work. Create unique naming conventions or create business rules to ensure that your files are sufficiently unique so that you don't accidentally overwrite them from another pod. So file storage. Here's a definition of a pod. And right here we have volume mounts. So I'm specifying the name of the volume, and this can be any name. In this case, I've named it the volume. And the mount path in container to dir, this is where my application assumes that this data will be. And it's any folder that I'd like. In this case, here's that path to where my application assumes that that data will be. And where is it actually going to be? Well, here in the volume section, the volume, the same name that I defined above, it will specify the type of driver, so in this case, host path, and the actual path to that content. Now, in this case, I said /mount/host path to dir. That's where the files will actually get stored. Now, the cool thing is there's the physical path. Here's that that symlinked path. And the container, the application, can just use it. It doesn't need to know where things are actually physically stored. Now, host path here is interesting because it stores it on that node that hosts the container. Now, that probably isn't a great place for production containers where I have multiple nodes in my cluster, but it is a good place to test. And it's really compatible across Docker runtimes and Kubernetes runtimes. But if you get into production, you probably want to choose a different driver. Maybe you'll choose Azure Blob Storage or Amazon S3 to store your content. So here's file storage. But then the magic question is, well, who owns this file? Should it be owned by the developer? Because all the rest of the pieces in this file are owned by the developer. You know, the image name and where in the container do we expect it to mount it? Or should it be owned by operations? Because operations knows where the durable file storage is, makes sure it gets backed up regularly. So who should own the file? We argue about similar things with web configs and things like that. Well, Kubernetes has thought of this and has a great mechanism to separate these into separate pieces so that we can have different pieces owned by different teams. So we have a hard drive here, and I'm debating putting a light on this image because I think that could be really cool. Here's our hard drive, and our hard drive gets carved up into little pieces. Here's our storage, and let's call each piece a persistent volume. Now, that persistent volume is a subset of this overall storage piece, and it doesn't need to be exactly the same size like it is in this piece. But let's say we've got all of our persistent volumes. Maybe they're, 10 gigs each. Now let's take one of these persistent volumes and let's check it out. Let's claim it. And as we claim it, we'll attach it as that symlink into the container. Now the container has a folder, but the container is actually a persistent volume claimed from a persistent volume, which is a piece of that storage on the hard drive. Now that's really cool. We have storage, persistent volume claims, and pods and containers. What's interesting now is that the developer can own the container and the pod, and they can also own the persistent volume claim. They know where that symlink needs to be. And operations can own the storage and the persistent volume. I'm going to carve it up into 10 gig spots, and you don't need to know where they're actually stored. You just need to know that they're 10 gigs. So that's perfect. Ops can own the physical storage. Developers can own the linking it into the container. And that clear separation of duties is native inside the Kubernetes operating system. Storage, persistent volumes, or maybe PV, persistent volume claims, maybe PVC, pods, containers. That's really cool. That separation of concerns allows us to make different choices based on the needs of our organization. So here's that persistent volume declaration where ops would define what these are. And here's that path. We saw that host path and the path on the physical directory. Here's a storage, the amount, the capacity, in this case 10 gigs, and a storage class name where we have the particular types of storage. One of the things that's really interesting here is the access modes. This is read write once. That means only one pod can connect to it at a time, and the pod can write to it. We have read write once, read write many, where many pods can connect to it, and we have read only, where pods can connect to it but can't write. So here's our persistent volume. here's our persistent volume claim where we're looking for one. In this case, we're asking for 3 gigs of storage, and we want it to be read-write once. As long as we have a match between the storage class name, the access modes, and at least that much storage, then that volume claim will claim that persistent volume. So that's perfect. We have this PV claim, and now in our pod definition, we can say instead of the volume just being a host mount path, we can say it's a persistent volume claim, and its claim name is PV claim, referencing that previous thing. We still have the same volume mounts identical in our pod, but now we're referencing that, for lack of a better term, foreign key off to that persistent volume claim. So a developer can own this pod definition, specifying the details in their container. They can own the persistent volume definition, specifying how much storage they need. Operations can own the persistent volume, specifying how that data is actually stored. That separation is perfect. Storage, persistent volumes, persistent volume claims, and linked into the pod as a volume. That's perfect. Any questions so far? So we saw in file storage how we can do that separation of concerns so that devs can own the pieces that are specific to the application, and operations can own those pieces that are specific to persisting and storing and backing up and validating. And that's perfect. We'll see that methodology as we go through each of these pieces, where Kubernetes has that nice separation of concerns if we need it. If we don't need it, then that simple case will work just fine, and we can just define it all in one place. Let's look at ConfigMaps. ConfigMaps are the way for storing configuration data. This configuration data could be the credentials that we need to get into our database, or the path on the file share that we need, or what domain name are we listening to. Here's a config. These are read-only configuration details. We can mount them either as environment variables or as files. So here's a configuration, a config map, or rather, here's configuration data directly in the pod. I'm specifying other things associated with this, but in addition, I'm here's my image, my name. I may specify resource limits. I may specify other content. And then I have this environment section. Here in this environment section, I have the names and the values that I would like for these environment variables. Now, the cool part is my application then looks for an environment variable named the message, reads that environment variable and whatever makes sense for my application's framework, and it gets that value of hello world. That's perfect. Now, here in this naive case, we've baked that configuration into the pod definition. But again, who owns this file? Should devs own it? Should ops own it? Well, probably these values are specific to the environment and they should be separate. We don't want to check in this one definition for all of the things. And so we have that same separation where developers can own the pieces specific to the application and operations can own the pieces outside the application, keeping the cluster healthy. Here's a config map that does exactly that. In this config map, we specify the name of the config map and then keys and values. So for example, in the config map, we have a key of database and we have a value of memSQL. Logging is true, so we've turned it on. API URL, here's the URL of that API that we need to call to get out our database. Well, that's perfect. Now in the, as we map that config map into our pod definition, we can do it either as environment variables or as files. Let's first take a look at doing it as environment variables. So here's that environment variable section, but now instead of just saying env, we say env from, and we specify where those things live outside of this container. So here's that config map reference, the config map, and that's the name of the config map that we gave it in the config map. So the pod is able to look up the config map and map in all of the keys as environment variables into our application. Our application can read those environment variables, and it has no idea that they were defined as a config map or inline. So they work identically. That's perfect. By contrast, we could also choose to map ConfigMap as files. So now here we create a volume mounts. Here's the volume and path in the container to dir. Inside that directory, we will have a file for each of the configuration details. My application can open that file, get at the content within that file, and then use that as the configuration details. Similar to the way we mapped volumes when we were looking at persistent volumes and persistent volume claims, now we specify that this came from a config map, and here's the name of the configuration map. So now our application just opens those files, and all the configuration details stored by operations are available to my application. That's perfect. So there are some portions of config maps that we probably want to keep more secret. Rather than just having them all open, these secrets will get encrypted. Now, the interesting piece is these were encrypted at rest, starting with Kubernetes 1.13. We're on 1.18 right now, so it's been a while. All of your clusters should now be able to support this. But before that, they were just stored as base 64 encoded. Oops. Now, we need to have all of these secrets available on every node in the cluster in case one of the nodes wants this configuration data. So it's possible that if we lose one of the nodes in our cluster, that we might lose those secrets if we're using a cluster older than 1.13. Starting in 1.13, they are stored encrypted at rest, so it's better. It's still not great though, and so you may choose to actually store your configuration in a key vault and have your application go log into that key vault to get at configuration secrets instead. But if we're going to use these secrets, we can do something like this. Now here's a YAML file specifying those secrets. I specify the name of my secret and then the keys and values for the secret. So here's a database username and a database password and the respective values that I'd like to pull up when I read this secret. Now I could create it in a YAML file like this, but it would be really easy to accidentally check this YAML file into source control and to leak my secrets. Now maybe I only check in the dev safe secrets, but probably I'm going to specify API keys and keys and tokens and those types of things. And so having them as a YAML file like this is pretty dangerous. Instead of specifying it as a YAML file, you can specify it on the command line as a secret this way. So I'm creating a secret called DB connection, and now I'm specifying my name, my keys and values for all the keys and values that I would like to be part of the secret. And that's a better way to store this information so that I'm not grabbing these secrets and accidentally committing them into source control. Now, there is a mechanism where I can either pipe these in from a file or otherwise protect them from my bash history, or once you finish running this command, go delete that line out of your bash history. So that's a mechanism where you can avoid committing these to source control. The cool part is now these secrets can get mapped in as environment variables or as files in the same way that we did with ConfigMaps. So here's how we would do it as files. I have the same container definition, and when I get to volume mounts, here's that volume mount. It's named the volume. As I'm defining how that volume works, I list the secret and the secret name. So here's that DB connection. Now, I'm not specifying all of the keys and values here. It's going to create one file per key in that folder. So I don't need to enumerate them. That's pretty cool. Similarly, if I wanted to map them as environment variables, I can specify each environment variable that I want this to be a secret key ref, what's the name of that secret, and what's the key within that secret to get at that environment variable. And now my application can read that environment variable in the way that it normally does. So that was really cool. We dug into configurations and we dug into secrets, and we saw how we could map them either as files or as environment variables specifying the particulars of the data in that config map or that secret that could be owned by operations. That works out really, really well. Any questions so far? Well, this is great. Let's dig into StatefulSets. We're getting through in record time. This is fun. So StatefulSets allow us to create a bundle of machines that work together as a cluster. Now, we do have a Kubernetes cluster. And so as we talk about, a cluster of machines, this can get kind of weird. So let's use an example. Maybe we have a database like a MemSQL database where we have lots of nodes that need to connect to each other. Or maybe we have an Elastic database where we need to keep different pieces of the data in different places. Or maybe we have a Kafka system where we need to create that Kafka pipeline. And all of the machines need to be able to talk to each other so that, for example, the Kafka server can get at the Zookeeper instance to know where its configuration is and all of the other instances. In this case, in each of these cases, we have a bundle of machines that need to know how to discover each other and identify that the other machine is up, or if it's down, take corrective action to ensure that the bundle of machines works together. We can think of this as a deployment, but with predictable machine names. With a deployment, as it spins up the pods, it gives them a random name. With a stateful set, as it spins up the pods, it gives them sequential names, 0, 1, 2. And so now I can discover the other machines in my stateful set because I know that name. So stateful sets, we talked about a Kafka cluster, an elk stack. I may have a MemSQL database where I have lots of different machines storing different pieces of my data. That can be a great use case for stateful sets. So stateful set, I have my containers, I have my pods wrapping them, but now I have a headless service that allows me communication between things. So if I want to reach out to any machine in my application, then the headless service works like it normally does, round robining across all of them. But if I want to specifically reach out to pod 1, I can reach through my headless service to pod 1, and now I've gotten to a very specific machine in my application. So headless service. Here's a stateful set that just defines all of the things. And if you squint real hard, yeah, it's pretty much a deployment. The only difference is it says stateful set, and it has this service name listing that headless service. And that's the headless service that the stateful set will use to communicate between machines. Everything else is pretty much a deployment. As I define that headless service, what makes it headless is the cluster IP of none. So it doesn't have a cluster IP, it doesn't have a node port, it isn't of type load balancer, it is of type headless. It has a cluster IP of none. So now if I want to get at any machine in this service, it's doing round robin across all of the applicable pods in the same way that any service would, then I can reach out to DB service, the name of my service. But if I want to get to a specific machine, I can grab the db1.db service or the db2.db service. And that's the mechanism that I can use to get to a specific machine in my headless service. Now, we could create this headless service to be able to connect for other purposes, and they could just hit it at DB service, but probably we want to only expose a subset of our cluster to callers. And so having a different service that only round robins to that portion of our stateful set would be a better mechanism. It's usually better to have a stateful set headless service specific to the stateful set and have a separate normal service that exposes my cluster to other consumers. So we were able to look at all of the pieces inside of our application. And as we built up our system here, we kind of take a look at all of the pieces. We have our service that round robins across our stateless pods and containers. We have an ingress that does DNS for us and allows data to get into our service. But we also have a domain. That's probably a config map. We have our HTTPS certificate. That's probably a secret. To that end, we may want to put the domain in the secret too if we wanted to. How does the pod know how to get to the database cluster? Well, here's some other config maps that identify the URL, the user, and pass, or maybe those are secrets. We can definitely mix and match them. We can have both secrets and config maps. Then how do I know how to get to file storage? Well, the file storage will have a persistent volume, and then we'll have a persistent volume claim mapping that into a directory inside of our pod. And now we have durable storage, and we also have access to it with PVs and PVCs. Our database cluster will have multiple machines that need to be able to talk to each other, and that's where we have a stateful set. The stateful set is able to, with the headless service, is able to discover the other machines and ensure that that bundle of machines stays healthy, spinning up new replacement machines if some of the pods or containers go down. So we saw how we can get all of the rest of our application up into Kubernetes using these mechanisms, these stateful mechanisms. Any questions so far? Well, this worked out really well. We can take the rest of our application and move it into Kubernetes using StatefulSets, using config maps and secrets, using persistent volumes and persistent volume claims. And now we're able to do stateful Kubernetes. What are your questions? It looks like we don't have any questions here in chat. If you're watching this on YouTube later, you can definitely tweet me at Rob_Rich. You can grab these slides right now on robrich.org and click through any of the blue links to be able to get at the content behind it. Thanks for joining us today. Thanks for joining us at Code PaLOusa.